each 20 by 20 then, we will create a histogram, then represent the histogram as a vector. So each 20 by 20 will be represented by what? One array of 58 numbers, right? So if I have total of 25 cells over here, because I divided the whole image into 25 regions, then what will be the total number of features over here? 58 coming from each cell, right? And how many cells? 25. So whatever that number is. Now that we will feed into, for example, a neural network classifier, where we may have, let's say, 100 neurons over here, 40 neurons over here, and now we train it on this part. So every input image, we get 58 by 25 features, feed it, we linearize them, feed it to our neural network, train it, and see how accurate it will be. Okay? So surprisingly, for face recognition, such a simple feature extraction technique works really well. Okay? So, so you guys will be able to test it and see it. Okay.
What is the expected output accuracy? It's more than 90, right? Expected accuracy for this structure.
Expected what?
Accuracy.
Accuracy? It should still be more than 90%. Yeah. It will be better than actually PCA. So PCA was giving us 90%, so this may give us 91, 92, something like that. Okay. Yes?
When we applied this technique for 3 by 3, it gives me 2 power 8 patterns, right?
No, when you apply it on a 3 by 3, you get one pattern.
Yeah, one pattern and the...
So see, like if you have a lot of numbers here, right? Your window is 3 by 3. So you are comparing the center pixel with all the 8 pixels, so you get one binary number.
Yeah, and the...
Then you move the window 1 pixel to the right. So if this was 100 by 100, right? Yeah. Theoretically speaking, you'll get 98 by 98 patterns. But what I'm saying is, we break our input image into 5 by 5 cells. For every cell, which is a 20 by 20, we'll apply the LBP. So obviously this will give us 18 by 18 LBP numbers, like 8-bit binary numbers. Then we convert these to a histogram. How many of these are uniform, and what is the frequency count appearing in that region? And so each of these 20 by 20 gets represented by 58 numbers.
Okay, so what did we mean by 2 to the power 8?
Because each pattern is a binary number, right? Because once you compare it with the 8, it will be like some number like this. So in 8 bits, how many total combinations are possible? 2 to the 8. So there are 2 to the 8 patterns possible. Okay, out of those 2 to the 8 patterns, some will be uniform, some will be non-uniform. So the non-uniform, if you count them, you just list all 256, then see where 2-bit change is occurring, where 3-bit change. So you'll see only 58 of them are uniform. So then you're counting the number of times a particular uniform pattern is occurring in each cell. And that's the histogram.
So this 58 is out from 256. We use this 58.
Right, because okay, first all you're doing is in this cell, 20 by 20, you're creating this many 8-bit numbers. Is this part okay? Because we are moving 3 by 3 window, each time you have a 3 by 3 window, it will give you one 8-bit number. Okay, then you take a look at it and see, is this uniform or not? Only if it is uniform. Okay, let me give you an example. Suppose you put a 3x3 window somewhere in the middle or somewhere here. You compare it with the center pixel with everybody else. You came up with this answer. Okay, so is this uniform or is it not?
Here it is uniform.
How many changes?
2.
2, right? And what's the value? 15 as an example, right? So now suppose this, if I list all the uniform pattern, is 0, 0, 0 a uniform pattern? Yes. 0, 0, 0, 1 is a uniform pattern. Let's pretend this happens to be pattern number 11 or pattern number 12. Okay? So now this value appears here, but if I move the window somewhere else, also it appears. Pretend 3 different places this pattern appeared. So for pattern number 12, I'll say the count is 3 in the histogram.
Yes. Okay.
Make sense?
What from this? What do you linearize to feed into the hidden layer again?
Okay, for each cell over here, we'll create a histogram, right?
Correct.
Histogram is basically 58 numbers with some may not even occur, so we'll put 0 there. Some may occur 5 times, so we'll put 5, right? So 58 numbers corresponding to the first cell.
Right.
Now we go to the second cell.
We do the same thing.
58 numbers corresponding to the second cell. 58, 58. We linearize them, so as you can see, this data will be basically 58, 58, and 58. And how many total will this be? So that's what will go to the neural network.
But in order to do that, we need the list of uniform patterns.
You need the list of uniform. I'll provide you the code.
Okay.
I'll provide you the codes to save time for you guys so that you give it an image. I will give you the 58 numbers. I'll give you the code for the neural network in C#. This code for LBP will be in C#. But of course you will read it, try to understand it nicely. But your job will be put the 2 pieces together and see what the accuracy is. Right? Piece of cake? Okay. So then, if you guys can try to get this far, then like I said, the most advanced recognition will be done through Siamese networks. So I'll come to the Siamese after that, and the deep learning we already discussed. So then your following assignment will be applying the Siamese network to do the highest possible recognition. And then you'll see how that works, right? Then, like I said, I'll go back and show you some object detection techniques based on classical methods. Then we will take a look at object detection based on deep learning, so that by the end, like I said, you have a complete picture of classical as well as deep learning techniques, and then I will tell you where the future is, and that's the goal for the next few weeks. Okay? So keep working hard, try to get this done as fast as possible. I'll try to put the code hopefully later today, if not today, by tomorrow. I'll stop here.